Okay, so today's section 9.5 is actually rather small. So 9.5 on representing systems. So what exactly is a system? It's a great question. Basically, let's start with the definition of a Markov chain. M-A-R-K-O-V. A Markov chain is a system in which the probability of each event depends only on the state of the previous event. So a system is a collection of, of events. A Markov chain in particular, and it's the only system that we're going to be dealing with, is a collection of events where each event has multiple possibilities. The example that the book uses, which we'll use as our demonstration, is whether it's wet outside or dry outside. So the book says, okay, today it's either wet or dry. Tomorrow it's either wet or dry. The day after it's either wet or dry. The day after it's either wet or dry. Each day is an event. A true Markov chain is one in which the state of an event, dry or wet today, doesn't depend on what happened a week ago or 10 days ago or even 2 days ago, but only depends on the state of the previous event and nothing else. That is what a Markov chain is, okay? So we have the following example, which we're not going to go into the details of where these numbers came from because they're not really important, but essentially we have the following possibilities. If it's dry, then the next day could be either dry or wet. And the claim is, for this example, that there is a 60% chance, a 0.6 chance, that if it's dry today, it will be dry tomorrow, that if it's dry during one event, it'll be dry for the next event, and a 40% chance, if it's dry today, that it'll be wet tomorrow. What if it's wet today? Then what are the likelihoods of being dry or wet tomorrow? In that case, the data seems to suggest for this particular contrived example that it's 0.5 or 0.5. These are what are called, these are the transition probabilities. The transition probabilities. They are the likelihoods of transitioning from one event to the next, state to state, dry to dry, dry to wet, wet to dry, wet to wet. We can also represent these in a transition state diagram. A transition state diagram. The only two possibilities are wet or dry, which the book puts in circles, wet or dry. To go from wet back to wet is a 0.5 probability. To go from dry back to dry is a 0.6 probability. To go wet to dry is a 0.5 possibility, and dry to wet is a 0.4 possibility. There's nothing new here that we didn't already have in the previous tree diagram. It's just a different way of representing it. And finally, we can represent it in a transition matrix. And this is, of course, why it's in this chapter. This chapter is all about matrices. How do we represent it in a transition matrix? Well, in this case, since there's two states It's going to be a 2 by 2 matrix. The current state will be represented by the columns, in our case, either dry or wet. The future state will be represented by the rows, either dry or wet. So dry to dry, 0.6. Dry to wet, 0.4. Wet to dry, 0.5. Wet to wet, 0.5. Again, no new information, just another way of representing it. Be aware, one thing that's important, if it's a valid transition matrix, note, columns must add to 1. If it's a valid transition matrix, the columns must add to 1. 0.6 plus 0.4 is 1. 0.5 plus 0.5 is 1. Why? Because you got to go somewhere. If you're dry today, you're either dry or wet tomorrow. It's got to be one or the other, because those are all the possibilities. And similarly, if it's wet, you have to go dry to dry. Okay, so let's now do an example. It says, Dockless Bicycle Company, MathBike, hires bicycles in a city through a mobile phone app. Users can unlock a bicycle with their smartphone, write it to their destination, and then lock the bicycle. MathBike divides the cities into 3 zones. There's inner, there's outer, so this is inner, there's outer, and there is central. So you have the inner zone, the outer zone, and the central business district. 3 areas. By tracking their bicycles with GPS over several weeks, the company finds that at the end of each day, 50% of the bicycles rented in Zone C remained in Zone C. So part A is going to ask me for a transition state diagram. I'm going to start it immediately. 50% of the ones from Zone C remained in Zone C. 30% of the ones from C were left in Zone I. And 20% were left in Zone O. 60% of the bicycles rented in Zone O remained in Zone O. 30% were left in Zone I. And 10% were left in Zone C. 35% of the bicycles in Zone I remained in Zone I. 35% were left in Zone O. And 30% were left in Zone C. So part A says, show this information in a transition state diagram. I already did. Part B, show this information in a transition matrix. Okay, well, for the matrix, I do have to label the rows and columns by I, O, and C in this case, but I get to pick the order. So I'll just do the order of the book. C, then I, then O, C, then I, then O. C to C is 0.5. C to I is 0.3. And C to O is 0.2. I to C is 0.3. I to I is 0.35. I to O is 0.35. O to C is 0.1. O to I is 0.3. And O to O is 0.6. So C, it says, determine the probability that after 3 days, a bicycle that started in C is now in O. So C to something, to something, to O. We're looking for the probability that if you left a bicycle in, if you rented a bicycle in Zone C, that after 3 days, it's going to be in Zone O. Now, if you didn't use matrices here or have Markov chain theory, which we're not developing, we're just going to use it, this could be a rather difficult problem. But this is the beauty of Markov chain theory, that all we're going to do is take our transition matrix T, and we're going to look at it to the third power, because the matrix represents the transition from one event to the next. We want 3 transitions. So what we're going to do is transition, transition, transition 3 times, T to the third power. So let's take out our calculators. Let's edit a 3 by 3 matrix of 0.5, 0.3, 0.1, 0.3, 0.35, 0.3, 0.2, 0.35, 0.6, double check the math, 0.5, 0.3, 0.1, 0.3, 0.35, 0.3, 0.2, 0.35, 0.6, quit out. Matrix A to the third power. And we want to go from C to O. That will be first column, bottom left. First column, bottom left, to the probability of C to O in 3 transitions is approximately 0.377. The book says 0.441, another mistake. It should be 0.377. C to O is the bottom left entry. So with that under our belt, let's go to the exercises. That's all there is in this section. So let's jump ahead to exercise 9G. And as always, you should be doing them yourself before looking straight for the answers. So question number 1. For these transition matrices, construct the corresponding transition diagrams. Okay, so we have a matrix of 2 states, x, y, and we have 5 over 11. Underneath it is 6 over 11, adds to 1, of course. 1 over 5, underneath it, 4 over 5, adds to 1. So we have x and we have y, x to x, 5 over 11, y to y, 4 over 5, x to y, 6 over 11, and then y to x, 1 over 5. Part B has a 3-state transition matrix. 0.2 underneath it, 0.5 underneath it, 0.3 adds to 1, 0, 0.9, 0.1, 0.47, 0.53. So here's my A, here's my B, and here's my C. A to A, 0.2, A to B, 0.5, A to C, 0.3. B to A can't happen. B to B, 0.9. B to C, 0.1. C to A, 0.47. C to B can't happen. C to C, 0.53. That was question number 1. Question number 2. Here's a transition state diagram. We have C and P. C to C is 0.75, P to P is 0.8, C to P is 0.25, and P to C is 0.2. So it says this transition state diagram shows the findings from market research of the buying habits of consumers who shop weekly and buy either soft drink brand Kiko, C stands for Kiko, or Popsi, Popsi. I'm not a copyright lawyer, but it seems kind of obvious what's going on here. Anyways, for example, the probability that a person buying Kiko will buy Popsi the next week is 0.25. C to P, 0.25. Okay. A. Show this information in a transition matrix T. Okay, so T, it's 2 by 2, only 2 states. It doesn't make a difference if you do CPCP or PCPC as long as it's consistent, but the book does CPCP. So C to C 0.75, C to P 0.25, P to C 0.2, and P to P 0.8. Then it says part B, calculate T cubed. Okay, well, that's not a problem. Second matrix, let's edit a 2 by 2 matrix. 0.75, 0.2, 0.25, 0.8. Quit out, matrix. Square, take it to the third power. Hopefully I did the right one. I did the, yeah, I did the right one. Okay, good. So it's going to be 0.536875, 0.3705, 0.463125, 0.6295. So it says calculate T cubed, and hence find the probability that a person who buys Popsy now will change to Kiko 3 weeks from now. Popsy to something, to Kiko. A 3-state transition from P to C. P to C is the upper right entry. So the answer is the probability of P to C in 3 steps is equal to 0.3705. Again, relatively straightforward. Question number 3. Upon further research, it is found that a more realistic model is to create a third state, capital N, to represent a person buying neither Kiko nor Popsy. And this more realistic state diagram is provided. C to C 0.65, C to P 0.25, C to N 0.1, N to N 0.9, N to C 0.05, N to P 0.05, P to P 0.7, P to C 0.26, and P to N 0.04. So A, complete the transition matrix T. Well, it's a 3 by 3, and the book is giving us the order CPM. It says completed. They gave me 3 of them, but let's just do all of them. So C to C is 0.65, C to P is 0.25, C to N is 0.1, P to C is 0.05, P to P, oh, I was looking at the wrong one. P to C is 0.26, P to P is 0.7, P to N is 0.04, N to C 0.05, N to P 0.05, N to N 0.9. Seems that people who don't drink either tend to stay that way. So part B, find the probability that a person buying neither Kiko nor Popsy now will buy Popsy 5 weeks from now. So probability of N to P in 5 steps. Well, hopefully by now we have the right idea here. We're going to make a matrix, a 3 by 3 matrix, 0.65, 0.26, 0.05, 0.25, 0.7, 0.05, 0.1, 0.04, 0.9, and then take this matrix to the 5th power, and we want N to P, which is 3rd column, 2nd row, so we get approximately 0.183. So there's an 18.3% chance that a person who buys neither now will buy Popsy in 5 weeks. Personally, I think the fact that you could predict these things based upon the model is pretty fascinating. All right, question number 4. It says a game begins in state 1 with 2 white coins in 1 box and 2 blue in another. Now, it says 2 blue, but the picture has red coins. So that's state 1. I'm going to move this a little closer. Okay, so this is state 1. 2 white coins in one box and 2 blue. You know what? You want blue, I'll give you blue. And 2 blue in another. That's state 1. A coin is chosen at random from each box and put into the other, and the process is repeated many times. So what are the other possible states that this system can be in? Well, it can be in the state that has 1 white and 1 blue in each box. And of course, it could be in the state that has 2 blues in the first box and 2 whites in the second box. Hopefully, it's fairly obvious that these are the only 3 states. State 1, state 2, and state 3. Part A. Construct the transition matrix to show the probabilities of transitioning from one state to another. So we want the 3 by 3 transition matrix, state 1, state 2, state 3, state 1, state 2, state 3. Okay, well, let's think about it. And you should definitely pause this and try to do it yourself before seeing my answer, 100%. Okay, so let's say you're in state 1. You take 1 coin from each box and you put into the other one. It is physically impossible to remain in state 1 because a blue one has to go to the first box and a white one has to go to the second. In fact, you must go to state 2 if you're in state 1. You can't go to state 3. You can't exchange 2 blues and 2 whites in one move. So the only possibility from state 1 is to go to state 2. Same thing with 3. The only possibility is to go from 3 to 2. There's no other possibility. Now, suppose you're in state 2. How can I go to state 1? Well, the only way to go from 2 to 1 is to remove a blue from the left and replace it with a white from the right. I need to take the white on the right and the blue on the left and replace them. That's the only way to go from 2 to 1. Well, what's the chance of picking the white in the left box, the blue in the left box and the white in the right box? It's a 1/2 chance and a 1/2 chance. So there's a 1/4 chance that occurs. And by symmetry, going from 2 to 3 is also a 1/4 chance. Because again, you got to remove one of the whites from the left and the blue from the right. Only one way to do that. Now, because the numbers in the column have to add to 1, I don't have to really think about this too much. It has to be 1/2. So that is part A. Now, the game is made more sophisticated by starting with 3 white coins in one box. 3 white coins in one box. And 3 blue in another. So now that's state 1. This is represented by 3W, 3B, 3 white, 3 blue. So what are the other possibilities besides this? Well, I can have 1 blue in the left. I can have 2 blues in the left, and I can have 3 blues in the left. So this is a 4-state system. State the new number of states, well, there's 4 of them, and construct the transition matrix T. So this is the 4x4 matrix because it's got 4 states. Okay, Now, you should, of course, again, definitely pause this and try it yourself. This is a lot of fun for people who think any of this is fun, but certainly you should give this one a shot. So, if you're in state 1 and you take 1 from each and switch them, you must go to state 2. There's no other possibility. Similarly, if you're in state 4, you must go to state 3. There's no other possibility. If you're in state 2, you can only go to 1 or 3. Well, I guess you can go to 2 as well, but you certainly can't go to 4. 2 cannot go to 4 because that would require a double switch, which you can't do in one step. So 2 cannot go to 4 and 3 cannot go to 1. So that's the easy part so far. Nothing says you got to do this in order, right? Do the easy parts. Do what you can. Okay, so now let's take a look. Suppose you're in state 2 and you want to go to state 1. You got to remove that blue, which is a 1 in 3 chance, and remove that white, which is a 1 in 3 chance. That's 1 in 9. By symmetry, that's also 1 in 9. Now, if I want to go to 2 to 3, I got to remove one of these whites on the left side and one of the blues. 2 out of 3, 2 out of 3, that's 4 out of 9. And by symmetry, 4 out of 9. And because it has to add to 1, the other one must also be 4 out of 9. And that is the transition matrix. Okay, now part C says investigate the transition matrices for other situations, such as 4 white, 4 blue, 5 white, 5 blue, 3 white, 2 blue, etc. This is a very rare situation, or I say skip. This is, problems fall into 2 categories. There's simple ones where you're just kind of getting a feel for the formulas. There's more complicated ones where you're really trying to understand what's going on at a deeper level and solve some more sophisticated problems. And then there's something like this. I wrote out the solution and it is not trivial. It's long, it's complicated. It's just, I don't feel it's appropriate for the level of this course. I recommend trying it 100%, see what you come up with, but I'm skipping it. So it's not going to happen often, but it is happening today. And maybe I'll make a video as a supplement after this, just with that problem alone. We'll see. Question 5, and the last question. It says 2 candidates, A and B, are running for an elected government office. Statistics gathered from a survey taken over several weeks prior to the election show that after each week, approximately 4.1% of the candidates who were planning to vote for candidate A changed their mind and decided to vote for candidate B. So I'm going to already start constructing my transition matrix here. It says 4.1%, so 0.041 of people who vote for A are going to switch to vote for B. And 3.2% of those who are planning to vote for candidate B are going to switch to vote A. That's 0.032. And because the columns have to add to 1, this is 0.959, and this is 0.968. So A. 5 weeks before, even before A, this is before A. 5 weeks before the election, a final survey showed 45,520 people are going to vote for A, and 38,745 people are going to vote for B. However, this is 5 weeks before the election. So there's 5 transitions where people switch, or stay. And the question is, after 5 weeks, right? So A, write a matrix equation that describes the number of voters supporting each candidate n weeks after the final survey. Well, if you take your transition matrix T and you do it n times, you transition n times, that will be the new transition matrix of people staying in A, B, and switching to B, B to A, and B to B. What do I do with that information? That's going to be a 2x2 matrix. I want to know how many people I have in each category. So what I'm going to do is I'm going to multiply that, and we'll see why this works in the next section. With all my complaints about this book, I mean, there's some great things about this book, 100%. I'm not saying it's horrible, but besides the typos, sometimes they will have questions just that are completely in the wrong place. And this is one of them. This question should be in the next section because they haven't yet explained that you can take this transition matrix and apply it to what is called a state vector. It's a vector representing the state that I'm in. I'm in a state with 45,520 people for A and 38,745 people for B. And then I transition and it gives me the new one. So this is the matrix for, this is the matrix equation for the number of people that are going to be voting for each one after n weeks. So for part B, it says, if this trend continues throughout the survey, what's the margin of victory? In other words, 5 weeks later, what are my numbers going to be? So let's go ahead and make a matrix, edit. We got a 2x2 matrix, 0.959, 0.032, 0.041, 0.968. And we are then going to take this matrix to the 5th power. And now I need a new matrix. I need a 2x1 matrix, which is 45520 and 38745. And then take what I had here and multiply it by this new matrix. And this gives me 42,812.7 and 41,452.3. Which means that approximately, well, not approximately, but the model suggests 42,813 for A and 41,452 for B. So not only does A win, but the margin of victory would be 1,361 people. So that takes us, so it says determine which candidate will win. A will win, and by 1,361 people. So that takes us to the end of section 9.5, and 9.6, we will continue on this, and then the real fun stuff in 9.7, and that'll be the end of the chapter. So we're almost there. So see you guys in 9.6.